All right, thank you very much for the introduction. Thank you for having me here at the Astronomy on Tap in Leiden. And today I'm going to be telling you about why size matters, and in particular how we can use the smallest galaxies that we have in the universe to answer some of the biggest questions, not only in astrophysics, but also in modern science. So to start with this talk, I wanted to give you a modern view of the universe, right? So how do we actually see it nowadays? So we know that the basic building blocks of the universe, or at least structure in the universe, are galaxies, right? So here you have an image of a galaxy. And galaxies are made up of many millions and trillions of stars, right? So they range in sizes from about 1 million stars to up to a quadrillion stars. So we're talking about a 1 with 14 zeros after that. So truly massive systems. And they come in various shapes and sizes. So the image that I have here, that corresponds to an elliptical galaxy. Even though it is formed by many of these quadrillions of stars, most of the light is, well, due to discrete stars, but because they're so small and there's so many of them, it looks sort of a diffuse galaxy. And this galaxy in particular has an elliptical shape, and normally most elliptical galaxies correspond to the most massive galaxies in the universe. But there's also different shapes, right? So for example, over here, that's the Sombrero Galaxy. I sort of find that a funny name, I don't know why. But you can see that it's more of a flattened distribution of stars. It has a very nice dust and gas disk, and yeah, completely different to the elliptical galaxy that we're seeing over there on the left. We also have dwarf galaxies, so here's a picture of a dwarf galaxy, and that's going to be the focus of this talk. It's going to be the smallest galaxies that we can observe in the universe, because those are the ones that we're going to use to answer the biggest questions that I'll describe in a second. And this one in particular is Fornax, which is nearby the Milky Way, which is our own galaxy. And you can see it's relatively, well, diffuse and spherical, right? So not anything like the other two. And then we have quirkier configurations of galaxies, right? So for example, here on the top right, you can see the so-called polar ring galaxy, where it's actually two galaxies that are undergoing an interaction, and that's sort of forming this weird configuration of stars, and truly is well, incredible to see these images. But by seeing all of this diversity, both in shapes and sizes, you may ask, are galaxies distributed uniformly across the universe, or do they cluster in a particular manner depending on the mass or the shapes? Right? You might expect galaxies that are undergoing interactions to be closer to other galaxies. And we can nowadays answer the question about how galaxies are distributed in the universe, because for many decades we've been mapping out the 3D distribution of galaxies in the universe. Okay? So this image over here, that corresponds to one such map, and it's done by its ongoing survey. And each dot corresponds to the position of one galaxy. Okay? And you can imagine the center, at the center of the plot, that's Earth, so that's what we're looking at. And the further you move away from the center, then the further away the galaxy is. What you can see is that on large scales, it sort of looks sort of this filamentary pattern, right? So that's called the cosmic web. And you can see all of these filaments, at some point, they crisscross and they form these higher density regions. But you can also hopefully see, which might be a little difficult, void regions. So these are regions where you don't really find many galaxies. Okay? And just to give you an illustration of one of these high density regions, this is an image of a cluster of galaxies. And these clusters of galaxies correspond to the most massive structures that we know in the universe, and they typically contain between hundreds and thousands of galaxies, all interacting together and essentially forming a little bit of a chaos within the region. So a question that naturally arises by looking at the distribution of structure on large scales, and also the diversity of galaxies, is what drives the formation of galaxies and the structure that we see in the universe. Right? Obviously gravity is going to play a role, but what is the source of gravity? Is it just the stars that we see that are driving this formation, or is it something else? Well, it's relatively simple to answer. The only thing that you need is 700 million euros. You build a telescope, you put in a rocket, you launch it to outer space, hope it doesn't blow up on the way there, and then you spend a few years taking an image of the so-called cosmic microwave background. So essentially, the cosmic microwave background is radiation that comes from very early in the universe, about 300,000 years after the Big Bang, that is essentially emitted, well not emitted, but we receive it in the microwave wavelength, similar to a microwave that you have in your kitchen, for example. And then what you can do is measure the temperature of that radiation as a function of the angle on the sky. So this is what this image is showing, where the red dots correspond to hotter regions, and then the blue spots correspond to colder regions. And even though it doesn't look that impressive, you know, it just sort of looks a mess, if you do a statistical and physical analysis of this image, what you can obtain is a lot of constraints on what the contents of the universe are. And if we do the analysis, what do we find? So what we find is that the baryons, which baryons are basically normal matter, so Earth, stars, gas, dust, you, me, it only makes up about 5% of the total energy density in the universe, so really a minuscule part. We also have dark energy, so that's about 70%, which is this sort of mysterious component that's kind of worms, and we're sort of still trying to grasp and understand it. But in today's focus, I'm going to be talking about dark matter, which makes up about 25% of the total energy density in the universe. And I'm going to be using the dwarf galaxies that I mentioned earlier to sort of understand dark matter and what it is. But before I go to that, I wanted to sort of give you a brief overview of what dark matter is, what we know about it. So dark matter, I've mentioned that you can infer its existence based on the cosmic magma background, but that's not the only evidence that we have for its existence, right? For example, if you take an image of a cluster of galaxies, so this is what's shown here on the right-hand side, you can see some of these features that are sort of curved, and they're curving around the most massive galaxies that you can see in the field of view. And the curvature that you can see is actually caused by mass bending light. So this mass is making this system act like a gravitational lens. And by doing a physical modeling of this gravitational lens, what you can obtain is the total mass of the system, which then, if you compare to the mass that you would obtain based on just the stellar light, you can see that there's a mismatch. There's a lot more mass that you can see. And that extra mass is what we call dark matter. And dark matter has actually been inferred, because it hasn't actually been directly detected in a lab, has been inferred for 90 years. Right? So the first paper mentioning dark matter explicitly is by Swiss astronomer Zwicky, and this is from 1933. So it really is almost a century of sort of knowing about dark matter, but we haven't actually detected it. So it's really one of the fundamental problems of modern science, well, both 20th century and 21st century science. But how do you actually constrain that which you cannot detect? Right? So for that, we resort to this thing called forward modeling. For those that don't know, I'm going to explain it using the example of a cake. All right? So imagine your grandmother has a cake. Chocolate cake is very nice. You know, you would like to know how to make it, but by whatever reason, she doesn't want to share the recipe. Right? So she just wants to keep her cake recipe so that she has all the highlights and so on. Even though you don't have the recipe, by experimentation, what you can do is trying to constrain what the actual recipe for that wonderful cake is. Okay? So for that, you need some educated guesses as to what the ingredients go into that cake. So obviously, you need some chocolate, but you don't know the brand. You need some sugar, so brown, white sugar, eggs, flour, vanilla. And if you're feeling a little bit cheeky, you can also add a little bit of brandy. Beyond that, you also need to sort of combine all of these ingredients using certain processes, right? So you need to whisk the eggs. How long you're whisking the eggs, that's going to leave a different consistency to the cake compared to not whisking them long enough. You also need to melt the chocolate. Are you going to add some milk once you melt it in the chocolate? And obviously, folding everything together in some batter. But once you've made all of the choices along this educated guess process, you get a batter, you put it in a tin, and then you bake it for about 2 hours. And what comes out? Okay, chocolate cake. But is it the chocolate cake that we want? We can go back and compare it. And we can ask the question, is my chocolate cake the same as chocolate cake? Well, we can ask, do they look the same? Obviously not. I don't know who made this cake, but obviously they don't look the same. Do they smell the same? You know, do they have a vanilla smell or more chocolatey? Do they taste the same? Do they have the same consistency? So by asking all of these questions and sort of taking all of them, we can narrow down the possibility of the ingredients and the processes that we need to make grandma's cake. So that's basically what we do in astronomy, to answer the question of what dark matter is. But now, we're talking about the universe. Right? So in terms of ingredients, we have lambda, which is dark energy, so mysterious force that makes up 70%. We have dark matter that I mentioned before, 25%. But also, we have the baryons, right? And baryons correspond to, for example, stars. This is dust that we see in the Milky Way, and also some gas. Right? So we put all the ingredients in our model. Then we need to add some processes. So for example, star formation, so this is an image of a star-forming region, and you can see many blue stars, which correspond to younger stars. This is why we know that it's a star-forming region. We also need to put other processes such as supernova feedback, which essentially is when a star dies, it goes bang. and that's what it causes. So it causes big explosion of energy, and that's what drives gas away. And then also we have other processes like black hole feedback. So these are supermassive black holes, right? So many trillions of solar masses that reside at the centers of galaxies. And these black holes, if they get hungry, they can swallow up some gas, and then that gas, they essentially drive these outflows and this energetic jets that you can see over here, which Philip would have talked about, so black hole jets. But unfortunately he's not going to be here, so I don't know when he's coming back, but you should listen to that. But once we set up our model, we just need to run the model. This time it's not in an oven, but rather in a supercomputer. And these simulations, there's a little bit, these simulations take about 6 million hours to run. Okay, so how do we put that into perspective? So with modern supercomputers, these simulations can take a few months to run. But if you were to do it in your laptop, say, it would take about 7 years. So not really a time scale that you would want to wait for a simulation to see whether something makes sense or not. And then once you have your virtual universe out, then you can ask the same questions as you do for the cake, right? So we can ask, are the distribution of galaxies in the real universe and the virtual universe the same? And this is what this image is showing. So on the top and the left wedges corresponds to the distribution of galaxies as observed in the years 2000. And then on the bottom right, in the bottom and the right, corresponds to the predicted distribution of galaxies. And what you can see is that both of them share this sort of filamentary structure on large scales, and therefore we know that at least we're not making something crazy. Right? So at least we're going in the right way in terms of the ingredients that we put in the model. But we can go even deeper and more detailed questions. So for example, are we obtaining realistic galaxies in our simulation or not? So, are they compatible with what we see in the universe? And you can take an image of real galaxies, so that's what's shown on the left-hand side. So the top is a very nice spiral disk galaxy face on. The bottom left corresponds to an edge on disk. And then you can go to the simulation, grab a galaxy, your favorite galaxy, and then you can compare it, right? So these two images correspond to the same galaxy, but one of them is seen face on, and the other one edge on. And then you can compare whether they're realistic or not. And in this particular case, well, it doesn't look too crazy, right? At least our simulated galaxy doesn't look like a potato, it looks like a disk galaxy, so yeah, that's okay. And something very good about this simulation process is that you can see the universe in a manner that you would not be able to see ever, right? So when you take a picture of the universe, everything is static because the timescales involved are so large. But in a simulation, you can just make a video, right? And what this video is showing is the evolution of a virtual universe from very early in the universe to the present day. And what we're going to do is we're going to zoom into this galaxy, and we're now viewing the gas that we put here. So you can see some clumps of gas being accreted towards the center. Oh, you saw some outflows over there. That corresponds to stars dying and driving these gas bubbles. Also the black hole is doing some damage. But you can see all of these gas clumps sort of coalescing towards the middle, and eventually over time they form a very nice gas disk. And this gas disk is going to eventually form stars, and this is what's shown here. So that's a very nice stellar disk that's formed in this simulation. And yeah, so the galaxy just continues forming stars, doing its own thing. You have a few smaller galaxies orbiting around it, dwarf galaxies. That'll be important later. And yeah, just sort of doing its own thing, evolving, so on. But yeah, you would not be able to see this in the real universe ever. And now we're approaching the present day. And now what we're going to see is a zoom-out view of essentially, this is the stars, a zoom-out view of where this galaxy is located within this cosmic web of dark matter and gas and stars. So now we're zooming out, you can see that's where the galaxy was, and as we zoom out, we're going to change to a grayscale, and these dark clumps, which are sort of connected by filaments, those correspond to dark matter halos. And we believe that dark matter halos are the hosts of essentially galaxies. So every galaxy that you see essentially should have formed in a dark matter halo. So it is essential to our understanding of structure formation. Now, how do we actually constrain dark matter? Well, we play the same game, right? So we have a model for dark matter, but then we can vary it. And by varying it, we can check whether we obtain a sensible universe or not. Right? And this has been done for many decades, but it's mostly been done on large scales. Right? So going back to the distribution of galaxies, what this plot is showing, each circle corresponds to a distribution of galaxies. V1, V2, V3 correspond to predicted distribution of galaxies. And then CFA, that's the distribution of galaxies as known in the 1980s. So, if you remember the image from the beginning, we've advanced quite a bit in terms of the maps of galaxies. But you could already see that based on this information from the 80s already, we could rule out the models that gave rise to these unrealistic distribution of galaxies. So that's sort of what's been done. But now the forefront is to use small-scale constraints to further constrain the nature of dark matter. And I'm going to explain what small scales mean, because small scale in astronomy is not really small scale. So what are small scales? Here I'm showing a picture of the Milky Way, right? And I've highlighted over here two smaller galaxies that are nearby. So those correspond to the Large and Small Magellanic Cloud, the SNC and LM2. And these are satellite galaxies of the Milky Way. And when we're talking about small scales, we're talking about galaxies that are near the Milky Way and that are smaller than the Milky Way, so satellite galaxies. And currently, we know about 100 satellites of the Milky Way, and the sensors and the lists of galaxies that we know around the Milky Way keeps on increasing with over the years. We'll also talk about essentially these things called stellar streams, which you can see. So on the y-axis, that's essentially position on the sky. On the x-axis, that's the position of the sky. So if you can imagine stars projected. And you can see this sort of very nice, thin and long overdensity of stars. And those are stellar streams that we believe are originated from these small galaxies being stripped by the gravitational field of the Milky Way. And I'll show some videos to sort of show that. But we don't only see this in the Milky Way, right? We also see it in nearby neighboring galaxies. So these are images of other galaxies, similar to the Milky Way, and you can see these sort of faint features around them, which correspond to stellar streams as well. You also see some shells, those are called shells, or umbrellas, depending on what you prefer. But we can see that the small scales are ubiquitous across galaxies in the universe, and therefore, if we can leverage this information, then we can constrain the nature of dark matter further. But before we change the nature of dark matter, let's consider what are the actual predictions in the normal vanilla dark matter. So here on the left-hand side, we focus on this image over here. That corresponds to the dark matter distribution as predicted near the Milky Way and Andromeda, which is another nearby galaxy to us. And you can see sort of these blobs of dark matter, so dark matter halos, and you can see that there's a few big blobs, and then there's many more small blobs. Okay? And if you remember what I said earlier, these blobs are going to be hosting galaxies, right? So if then we plot, okay, which blobs contain some galaxies, this is the image that you obtain. So you can see that, yeah, you have, for example, a Milky Way over there, you also have an Andromeda, and you also have a few of these smaller galaxies, which correspond to the satellites that we're actually interested in looking for. And if you select the stars associated to these satellites, and then you plot how they're distributed, then you can see that they form a lot of the features that we've seen before, right? So each column over here corresponds to a different realization of the Milky Way galaxy. The top panels correspond to examples where the stars are in a satellite-like configuration, so sort of compact, not very disturbed, and so on. The middle plot over here corresponds to satellites that have been stripped by the gravitational field of the Milky Way, and that's what's causing the stellar streams that we saw earlier, both in the Milky Way and beyond the Milky Way. And then finally, you have a population of satellites that, through the effect of the Milky Way, they were completely disrupted and destroyed. And eventually, the stellar distribution doesn't have many features and just basically a spherical blob. So not a lot of features there, but it still contains important cosmological information. Now, to go to the alternative dark matter models, let's think, okay, what do different dark matter models change relative to the normal dark matter model? For example, there's models of dark matter that change the amount of structure that you would predict around these Milky Way halos or galaxies. So on the left-hand side, that's a simulation of a Milky Way, and you're seeing the dark matter distribution, and this corresponds to normal dark matter, so you can see many clumps around here. But then if you change the model of dark matter, what you can see is that many of those smaller clumps have sort of vanished, right? So disintegrated. And only the most massive of them remain. And because dark matter halos host galaxies, you might expect that you would have less satellites and less galaxies in the right-hand model compared to the left-hand model. So that's something that we can look out for. Also, the model of dark matter can also affect the resilience of the Milky Way tidal field. Thank you. So on the left, so this is a video of an idealized simulation. So what I'm showing is the dark matter distribution. And on the left-hand side, that corresponds to a dark matter halo, a dark matter blob, that it has properties similar to what we would expect in normal dark matter. And then on the left-hand side, right-hand side, we have an alternative dark matter model. and they've been initiated with the same initial conditions, so the same sort of orbit, but the only thing that changes is the structure. And you can see that over time, the dark matter halo loses mass because of the gravitational tidal field of the object. And as they lose mass, they sort of become smaller and smaller, and by the end of the simulation, what happens is the normal dark matter clump that we started with still survives, right? So if it has a galaxy in there, you would detect that satellite galaxy. But on the right-hand side, it's been completely disrupted. There's no clump there, right? So even if you start with a galaxy in both models, one of them will be completely disrupted and lead to a featureless distribution. And then the one on the left, the normal dark matter, you'll have a satellite. So putting it all together, on the left-hand side, you can essentially plot what's the number of the accreted galaxies that you would have as a function of the mass or the luminosity. And then for different dark matter models, you would predict different numbers, right? So black, you can imagine that's the vanilla dark matter model that we have. But as I showed earlier, different dark matter models will suppress the number of small galaxies that you would accrete, and therefore the number of galaxies you would expect around the Milky Way. And then different dark matter models can also change how many of these galaxies you destruct and destroy, right? So, and again, this is the fraction of destroyed galaxies as a function of their mass or luminosity. So if you imagine one case where we saw the disruption, then you would see this curve being higher, which is what we see here, whereas a more resilient dark matter model will be a lower curve. And then putting all together, what you can do is predict the number of present-day satellites that you would have around the Milky Way, so the number of galaxies. And these correspond to the different curves that we have, and this is mass and luminosity. So this is a prediction, right? So different lines correspond to different dark matter models. So then what you can do is get a telescope, take images of the sky, and try to detect as many of these galaxies as possible. And this is essentially what it looks like. So we have some space telescope planning, we have already some observatories on Earth trying to do this, and also some Earth observatories that are being under construction that will be perfect for this kind of science. And what you obtain is a few data points, so the number of galaxies as a function of the luminosity. And once you put the data points on sort of this plot, then you can tell, okay, which dark matter model is realistic or not. So for example, the red and the purple curves over here, they're completely distant from this data point that we have, but so that means that they're not sensible dark matter models. And then the ones, the satellites or the galaxies that are too low luminosity, you wouldn't be able to see, but that's why you build better telescopes to detect these faint galaxies around the Milky Way. And by doing this iterative process, then what you can do is further constrain the nature of dark matter and further understanding of this big fundamental question in modern science. And with that, I'm done. I'll put a video of a simulation, and yeah, thank you very much for listening. Any questions, I guess?
When you compare the structure of the things you measure in the end of your simulations and what you measure, how do you compare what is very similar or not? Because many of them to me seem a bit just blurry and chaotic anyway.
Do you mean, okay, so the question was, how do you actually compare the structure of the things that you see between different dark matter models?
How do you say what is a good match?
What is a good match? Well, I mean, so, okay, sorry, I'll have to stop the video. So the good match essentially, I mean, this is the beauty in the approach, right? So the good match is basically counting up how many of these galaxies you have as a function of the luminosity. Then you have certain predictions for dark matter models. And then the ones that don't really match what you see, so the number count, for example, how many galaxies you have, those are not a good match. Of course, then you have some models that give you a very similar answer, and that's why we need to push into the really faint regime of dwarf galaxies and the smallest galaxies, because then we would be able to disentangle, right? So if I go to the previous slide, you can see that these models that look very similar on the range that we were probing with our observations, they may differ once you go to lower luminosity galaxies. So that's sort of the approach, right? So you always try to detect as many galaxies as you can, and then from there you can hopefully distinguish between one model and the other one. I'll put the video again, just watch. Yeah?
You were talking about different kinds of dark matter.
Mm-hmm.
What kind of different properties they have? The only thing we know about is gravity, and that should be the same. But what are the other properties in which they're different?
Yeah, so I was basically focusing on two different flavors of alternative dark matter models. So one of the key properties of dark matter is the mass of the particle. We assume it's a particle. But for example, if you have a dark matter model like the vanilla one, you would expect that it's very massive, which means that it can cluster a lot, right? So it will lead to a lot of formation of structure. Whereas something that's a dark matter model that erases all the structure, that's a much lighter particle, which means that very early in the universe is moving very quickly. So any sort of perturbations in the density that would eventually become galaxies, they're sort of smoothed over, and that's what leads to the difference at present day. And then there's another flavor of dark matter where dark matter particles can scatter over each other, sort of collide. And that one can lead to structural changes, so for example, the resilience to the fields of the Milky Way. But yeah, basically it's the mass of the dark matter particle and also whether the dark matter particle can interact. But yeah, I mean, it's a very crude approximation, right? I mean, we don't have that much information that we can take from that, but we're focusing on properties that we could, in principle, constrain using macroscopic observations.
Another question. You showed two kinds of simulations, one with a star, a very dense clustering of dark matter, and the other one who was fading out over time. Which direction is it going in your simulations? Are you already...
In terms of which model dark matter based on...
Which direction is it going in?
Yeah, so the direction it seems to be going is the vanilla normal dark matter model. So, not very exciting. But the thing is, obviously I simplified the process here, but there's a lot of uncertainties, a lot of complications. But within the uncertainties and the models that we have, it does seem like the normal dark matter that was proposed 40 years ago still does a good job, right? And you always want to choose the simplest model that fits your observations, right? So at the time when we see a difference between our normal dark matter predictions and observations, then we can consider, okay, do we want a more complex model of dark matter? But at the moment, yeah, it is more the vanilla normal dark matter model. Yes?
Thank you. So the dark matter, the goal is to determine the dark matter, nature of the dark matter.
Yeah.
And also the distribution of it, or just the nature?
Yeah, I mean, in principle, the nature influences the distribution. So what you want to do is measure the distribution of dark matter, but because you can't see it, you need to do that using galaxies, right? Because those are traces of the underlying dark matter, right? So every galaxy, well, not every galaxy, yeah, every galaxy in principle is at the center of a dark matter halo. So yeah, it's the other way around. So we want to constrain the nature by looking at the distribution of dark matter. Yeah.
You showed large-scale simulations of the universe.
Mm-hmm.
Do we have any idea where we are if we look to this type of structure? What type of environment we are living in?
Yeah, that's a very interesting question. So the question was, for those that couldn't hear, is whether in these simulations we could determine what sort of environment we're living in. And the answer is yes. Let me think about how to answer this. So what you can do is, for example, run a simulation, right? And you run a simulation such that by the time it finishes, it matches the distribution of galaxies that we have in the local environment. And then if you do that, what you can do is just literally go to the simulation and say, okay, is my local region the same as any other region that we pick out? And I think the answer is that we're sort of living in a underdense...
It's a d sigma of the
yeah, so a lower density. Yeah. So we're living in an underdense region of the universe, yes. Yeah. Oh, sorry.
I think you mentioned something about the starting point and the ingredients being relevant in the simulations. With the data that they're getting from the James Webb, did you expect any changes in when you put into your simulations?
Yeah, so the question was whether we would expect any changes in our models based on data from the James Webb Telescope. And then the answer is, at least from my understanding, I don't do really early universe science of galaxies. My understanding is that there's a lot of observational uncertainties, so not everyone is as confident in the interpretation of the data that's coming. But if there is a difference, then I think we would first need to look more at the modeling that we do of how galaxies form. Right, so that's something I haven't really touched upon here, but galaxy formation is a complex process, and I would be more inclined towards saying that we would need to revise our formation, our model of how galaxies form, rather than a fundamental change in sort of the nature of cosmology. Yeah.
Just maybe a very ignorant, stupid question. We have now the data from Gaia. Gaia, we know also the vectors and speeds of objects moving in our galaxy. Would it be a decent way to go backwards?
Yeah. So the question was based on Gaia, which is a space telescope that is able to measure essentially the position and the velocity of stars in the Milky Way, whether we can go backwards. And then the answer to that is yes, to an extent. And the way in which people go backwards is when you have all of these, for example, let me play the video. Okay, never mind. I don't think it's going to work well. But if you imagine one of these satellite galaxies, for example, being stripped by the Milky Way, it's going to deposit its stars in a particular velocity and position, right? And even though over time it mixes and you lose some of the information, by using essentially a statistical approach to the position and the velocity of the stars, you can constrain, for example, what is the assembly history of the Milky Way. Right? So now, for example, we believe that the Milky Way had a merger with another massive galaxy in the high redshift, and that leaves an imprint in the velocity distribution of the stars. People are doing that.
We know now how many arms we have. We know that our galaxy is basically a sausage with 4 arms. So at least an indication.
Yeah, I mean, for example, constraining the spiral structure of the Milky Way, that's a little bit it's more difficult because you have a lot of dust, right, intervening, which means that you can't really see the whole disk of the Milky Way. But for the purposes of the assembly history, these stars are deposited at relatively large distances from the center and also above the disk plane, which means that in principle you can observe them a little bit better compared to just measuring things through the disk where you have a lot of dust. Yeah.
How do you choose the ingredients for the chocolate cake?
How do I choose them? Well, I don't know, I guess experience. To be honest, I've never made a chocolate cake, so I just went with my gut. But I presume that's what people use, I don't know. If you have a better guess, then...
No, I mean bread for the
Right. Sorry, I got a little bit lost in the chocolate cake metaphor. Well, alright, so... in terms of the ingredients, right, so lambda, dark energy, and DM, dark matter, we sort of know from the cosmic microwave background that I explained at the beginning, right? And then in terms of the ingredients, well, you just take a telescope, observe galaxies, and see, okay, what are the constituents of those galaxies, right? And obviously, you can see stars, so that's an important component. You can see gas, gas and dust, and then, basically you take a telescope, you observe galaxies, and you see, okay, what are the components that we observe in these galaxies, right? So mostly stars, gas, dust, but then obviously you can become a little bit more particular about it or more detailed and try to ask what chemical elements and so on. But to sort of zero-level approximation, you can just observe a galaxy and then see, okay, what's it made of.
Maybe one last question before we end.
I have another question. You showed the animation of the dark matter halos. This is the dark matter moving. How is the galaxy on top of it? How does that?
Yeah, so the galaxy. So the dark matter halos, we believe, are many times larger than the galaxies that it hosts, right? So the galaxy is only a very tiny fraction of what you see here. And the galaxy, you can imagine, is basically at the center, basically, just like a point. right? So most of the mass that's being lost initially is just the dark mass, but eventually if you get to a point where you lose so much mass that everything is disrupted, then the galaxy at the center may disrupt, right? Well, be destroyed. But yeah, basically it would be very difficult to see at this scale where the galaxy is because it would be very, very small.
Really good to stop
Yeah.
there. Then
Thank
just
you.
thank our speaker again.